So
It
I've
is
been
coming.
moving in the next. Okay, it is coming.
Yeah, it's coming. Nicely, it is coming.
Fine. It is moving, right?
Yes.
Okay,
So
fine.
first slide you can put. Yeah, so that people
Yeah,
will
fine.
see about.
So how is going? All fine.
Yeah,
So busy
going
since
fine.
last.
And really, I'm very thankful that morning 5:30 you join. It's
It's
really
fine.
great. Yeah, really great.
We are all learning from you. So,
No, but usually people will not. They will tell that so early difficult sleeping time, na.
ah,
Then also you took so much pain for us. Really, we are grateful to you. So you are working there also in the domain of photonics.
yeah, broadly it is in photonics, terahertz photonics.
Oh,
Yeah.
so University of
So,
Leeds is having very good ranking, na?
yeah, it is around I think 75 in the
Wow.
yeah, I remember.
Under which professor you are working there?
So here we have like Professor Paul Dean. So it is a like a large group. Uh, the project is in collaboration with University of Cambridge and University College London, and
Very
broadly it
good.
is on quantum cascade laser, terahertz quantum cascade lasers for wireless communication, that kind of applications.
Very nice. Very nice. We we want to our participant want to listen more from you
Yeah,
because you are the live example. Nowadays, to get PDF or a postdoctoral work or after doctorate, it's really highly impossible.
yeah, it
I
is
am observing
challenging. Yeah, you're
because
right,
I
ma'am.
am trying for many my scholars. It's not so easy. So how you got?
So they like I applied like they have the vacancy basically. So I filled that vacancy. Then they took the interview and asked like
Very nice.
regarding the experience and if like fabrication stuff and what are the challenges I have faced uh, during the experiment, all those things, and
Mm,
yeah, like that.
very nice. Very
Yeah.
nice.
Excuse me. Sorry for interrupting. Sir, could you please adjust the camera? Half of your face is visible.
Okay, let me do.
Now it's fine, sir.
Okay,
Thank you.
thank you.
So you are working there in the lab or simulation work.
Yeah, it is experimental work. So the group works in modeling as well as experiment. So right now the work is starting. So maybe it should be like a combination of modeling, fabrication, and experiment testing. Yeah,
For the laser source.
yeah, we are like working on making here the like source as well as the detectors as well in the terahertz frequency.
Okay.
And yeah, so like because it's like 5 6 professors who are like actively working around in this terahertz. So broadly they are covering everything in the terahertz, like the manipulation of the devices and the control their property sources as well as detectors.
Asha madam. Hello.
Yes, ma'am.
Actually, I talked to principal, so he told in between or at the end of time I will join. So you
Okay.
start actually because DAC meeting is there in other
Okay.
department, so
Okay.
he is there present there. Okay,
Okay.
so
Okay.
formal way you can start and
Now,
write in a TOC group also.
Yeah. Yes, ma'am.
Somebody should write in a TOC group.
Yeah, I
Okay,
have posted it already.
TOC group.
Yes,
Okay,
yes, ma'am.
okay, okay. Now you can start.
Yeah. But only 30 participants are there till now.
Yeah, yeah. They will join. But
Okay.
we are always starting our talk by, we are very punctual. So it's exact 10 here in India. So we will start by time. Okay. They will join gradually.
Yeah. Okay.
Okay.
Ladies and gentlemen, good morning and welcome to you all to the last day of 15-day International Faculty Development Program on Quantum Computing and Sensor Technologies for Viksit Bharat at 2047. It is with great pleasure and honor that I, Professor Asha, Department of Computer Science and Engineering, stand before you to extend a warm welcome to our esteemed speaker, Dr. Deepak Kumar, Research Fellow at School of Electronic and Electrical Communication, University of Leeds, United Kingdom. Dr. Kumar's journey through academia and research is nothing short of inspiring. With a rich academic background and including a doctoral degree from the Department of Physics at Punjab University and experience working as a research fellow at the School of Electronic and Electrical Engineering, University of Leeds, Dr. Kumar brings a wealth of knowledge and expertise to our program. His professional journey has been marked by significant achievements and contributions to the field of physics. From his tenure as a project scientist one at CSIRO, to his role as a guest faculty at Guru Jambheshwar University of Science and Technology, Dr. Deepak has consistently demonstrated a deep commitment to advancing scientific research and education. Dr. Kumar's research on metamaterials has garnered international recognition, with his works being featured on the cover pages of esteemed journals and receiving numerous citations. His dedication to innovation and scholarly excellence is further underscored by his association with prestigious organizations such as SPIE, IEEE, OSA, and the Royal Society of Chemistry. Beyond his academic and professional accomplishments, Dr. Kumar's commitment to mentorship and knowledge sharing is evident through his engagement as a potential speaker at renowned institutions like the Indian Institute of Science and CSIR CSIU, as well as his extension lectures delivered at various educational platforms. Today, we have the privilege of learning from Dr. Kumar's vast experience and expertise in the field of physics. I am certain that his insights and perspectives will enrich our understanding and inspire us to strive for excellence in our own pursuits. Please join me in extending a warm welcome to Dr. Deepak Kumar. We are truly fortunate to have him as our speaker today, and I'm confident that his presentation will be both enlightening and thought provoking. Let us hear more about from the speaker himself. Over to you, sir. Thank you.
Thank you, Professor Ashaji and Professor Prita Saranji for the kind invitation and the Oxford College team for organizing this exciting conference and the faculty development program. So
Welcome, sir.
I'm going to start. So today the message is on metamaterials in photonics. So currently I'm working at University of Leeds, United Kingdom. Uh, yeah, so let me give
Deepak
it.
ji, Deepak ji,
Yeah,
before
ma'am.
you will start on your technical topic, just I will request you how you reach there, because our participants are really interested. They are sending me message that they all are interested for higher study. In that too in
Okay.
such a when you where you are have the collaboration with the Cambridge University and all. So that little bit you will put light and then you start your technical one. Okay, so that
Yeah,
people
so
will get benefit actually.
yeah, thank you, ma'am. So regarding the postdoc work. So of course you should have a PhD degree. At least you should submitted your PhD degree, or maybe you have a defense. You have completed your defense. Then you can start applying for the postdoctoral vacancy. So there are like online websites like I have used a scholarshipdb.net. Scholarshipdb.net, so where most of the vacancies are being posted, and you can like subscribe to that link, so that you can have a details of the vacancy directly on your email, or otherwise you can just browse on the website, so that you can have a list of the vacancies which are being posted there in different fields. There might be some other links also, and then you can apply for the vacancy. So normally you should have to prepare your resume basically, and maybe a cover letter showing the experience which you have gained uh, during your PhD, or from your prior experience, and related with the vacancy you are applying. So you have to basically defend yourself, how you are stable for any vacancy which you are applying through the experience which you have. It might be the case that you are applying for a vacancy, but you don't have so much experience in that field. It's okay. Still, I mean, you have to show like why you are motivated to apply, or why you are motivated to switch, if you're switching a field a little bit or quite large. So you have to explain like how your earlier experience will be helpful in this field, and how it can help in the group which you are going to join, right? So yeah, so so normally you can apply, then they ask you, if you're shortlisted, then they ask you for a presentation where you can discuss your work, and they ask you the questions regarding the experience and the work which we have done, and how you are thinking that you are stable, your experience is stable for the vacancy you are applying. So like that way, and yeah, it's all goes fine, and they let you in. That's how the things go. Basically keep trying. I mean, I also given like 4 or 5 interviews for my postdoctoral
So total,
vacancy.
how many months started and ending when you applied and you got it?
Right. So normally, like as you apply for a vacancy, so normally within 2 weeks period around, so they basically let you know about your, whether you are selected for the interview, and then they give you a date. Also, that depends on the, normally it depends on the your flexibility, like and after your interview, basically the presentation and the discussion. So then within a week, most probably, or maximum within 10 days around, so they will let you know about the results. So within, so roughly you can say within a month you are able to like get the final result for the vacancy. Yeah.
Yeah, very nice. So I hope participant will definitely get some insight into this. Yeah. So now
Yeah,
you can.
keep trying. Yeah, and because I also like, sometimes you apply for a, sometimes you can email also to the people which you know in the field, asking like, I have completed my PhD and I want to apply. So if they have vacancy, they will let you know. Or sometimes it happens they don't have the vacancy at that time, but they will let you know like in the next 3 or 4 months they have the funding and they have the vacancy. So you can apply via sending email personally to the researchers, or also there are like advertisements, like I have told you, you can apply straight to the advertisement, like that way. Sometimes you get the reply and sometimes you don't get the reply. So one thing that to be taken care, like the country which, or the researcher in a particular country you are targeting, let's say USA, UK, or Australia, somewhere. So you have to send the email according to their time zone, like, so that it will reach to them in the morning hours, in between 9 to 12, like in the morning, so that they will see your email on the top, right? So it will increase basically the maximum chance that they will see your email, and you will get a reply. Because it might happen like you send the email, and because so many emails they got, they are not able to see, or like that. So according, you apply according to the time zone of the country, so that it, the, like mainly in the morning hours, around 9 to 12 roughly, according to that. So it will enhance your chance of the response basically getting. Yeah.
Okay, okay. Thank you so much for giving the detail this one. Now we can start, and good number of participants also join. So now we can start our topic. Okay.
Yeah.
Now you can
Yeah.
start.
So thank you, ma'am. So today we are discussing on the metamaterials and the photonics basically. So I'm on the second slide. So I'm moving. Are you able to see right?
Yes, yes.
Yeah, okay. So this is a quick outline of the work, how the field has started and how the different metamaterials are being used in different applications in the photonics, and how the other what is the current status of the field. So yeah, so metamaterials basically these are the artificially designed structures. These are basically the sub-wavelength structures. So what you mean by sub-wavelength? Sub-wavelength means the basically the dimensions of these structures are basically lesser than the wavelength which is incident on the structure. So for example, uh, if the lambda is the wavelength of the light which is incident on the structure, so these structures should have dimension lesser than the lambda, like lambda by 6, lambda by 8. So these are basically the artificially designed sub-wavelength structures, and they might be periodic as well as non-periodic, and we are able to get the properties from these sub-wavelength designs which are not in direct access by the natural materials. So we have the natural materials, we talk about the fundamental constituent particle like electron, proton, neutrons. So if we are able to control the number of electrons and in the materials, right? So in a way we are able to basically control the property of that material. So in the similar way, if we design these artificially designed structures, and so if you are able to basically tune these structures in terms of the dimension, in terms of the different geometries, right? So basically we are able to tune the property of the device which we are going to make using these structures. So in a way, like the conventional materials, they are also provide us the flexibility to tune the property of a device. So this field started its journey in the beginning, where the Indian researcher, Indian scientist, Professor Jagdish Chandra Bose started working in this field. Earlier, that this word metamaterial is not coined at that time. Yeah, normally in the broad sense, the uh, artificially structures, that type of word is in the picture at that time. So he has initially started working in this field, where the twisted jute bundles he has used for the rotation of the light, basically. Then the around 1968 Vesselgo proposed a theoretical proposal for the negative index refraction phenomenon. And then slowly, after the theoretical proposal, the experimental study starts coming into picture, where the Pendry and Smith, and they start working and towards the experimental realization of this kind of materials, basically the metamaterials basically. So 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 various kind of new phenomena are being reported using metamaterials, like anomalous refraction, where the, as we study in our school days, the basically the Snell's law of refraction, so that gets modified. The basic science remains the same, the equation gets modified, uh, and that is basically anomalous refraction that is being basically named. And electromagnetic induced transparency, broad resonance excitation, narrow resonance excitation. Narrow resonance excitation is very helpful for the sensing applications, like phonoresonances, right? So extraordinary transmission. So there are new phenomena are being reported based on these structures, and you can see these can be designed in various shapes, as I've shown you some with some pictures, like circular shape, some scare which with a little gap in that. In different alphabeticals, you can say L and the twisted L, like that. So that again depend on the design, depending on the applications which you are targeting. So helical shape, basically the three-dimensional geometries, planar designs, right? So they can be tuned in different shapes, and accordingly you are able to get the functionality out of them, right? So this is a basically a metamaterial tree where you can see how basically showing a like how the fields is having a different kind of applications, like negative index, artificial magnetism. So you can see there are many apples in the tree. The red apples where the field is almost, I mean, it basically started in the beginning, right? So then slowly, so that gets because the fruits which are like fully developed, they get fall down, right? So that's why the red apples are in the bottom. So then you can see the yellow and the green apples. So those are the fields which are recently growing, like uh, transformation optics, then the switchable metamaterials, quantum metamaterials, nonlinear metamaterials, sensor metamaterials. Yeah. So these are the different domains which are in the field, which are in the active stage, right? So why we are interested in metamaterials? So what is the metamaterial, so why we are interested in the metamaterials? So if you see the electromagnetic spectrums, so that starts from high frequency gamma ray towards x-ray, visible, microwaves, so there is a region in the in this electromagnetic region broadly known as terahertz frequency. So that, as I have circled in this electromagnetic spectrum with the circle terahertz, right? So this region falls in between broadly in the microwave and the visible. So, or you can say broadly in the electronics and the photonics section, right? So this terahertz frequency region. So this is basic having lacking of the different applications. Why? Because we have a scarcity of the materials, we have a deficiency of the materials which are showing their signatures, spectral signatures in the terahertz frequency. So as you know, if you don't have the materials to show the signatures, then how you are going to grow the device? So in order to bring applications in the terahertz frequency regions, you should have the materials, and you should have the device which can respond right in the depth frequency. So then we started designing, fabricating artificially designed materials that are basically metamaterials, so that we can bring applications in this terahertz frequency region. So that is one of the reasons why we are interested in the metamaterials, specifically in the terahertz frequency. And the terahertz frequency has lots of applications, like in the imaging sector. So if like if someone is hiding some weapons, as you can see here in the picture, like some gun, so terahertz can be reflected from the metals, and you can basically check out where the weapon is. So as a in the security purpose, it can be used, and to track the terrorist and that kind of activities. And terahertz are having less energy than the X-rays, so they can be used to basically diagnose the tissues and the cells. So maybe in the coming time, as we go in the medical hospitals, so instead of the X-ray, we should have the terahertz uh, scanning system, right? And yeah, and like if we have the food items, and there is some metallic contaminants in the food, so we can have a like quality checking of that food items using terahertz, because terahertz can be reflected from the metal. So and also they can be used to study the astronomical objects, because an appreciable amount of the signals is being emitted from the galaxies in the universe. So you can study the evolution of the astronomical objects, the galaxies, basically using terahertz. So these are the few applications of the terahertz, as you can see, which are basically touching the different domains. Okay, so yeah, so let me go how the metamaterials are helpful in the terahertz. Let me go to the basic, then we'll see some applications in this side, right? So 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 you can see we study from our school days. So there is the crystal lattice or the atomic lattice, that word we have heard. So basically there is a unit cell, and if that unit cell gets repeated, so basically the unit cell is the basic element of a crystal lattice, right? And if you repeat the unit cell, you get an entire lattice. What do you mean by the repetition? It means you repeat the basic structure, the unit cell, in the, let's say, in the x direction and the y direction, then you get an array basically of that unit cell, and then array itself makes a lattice, right? So I have shown a simple diagram where a square ring is being shown in the yellow color, right? And there is a gap in the ring is put. So this ring is known as split ring resonator, because you have splitted this ring with a gap. So this is known as split ring resonator. Okay, so the yellow color is basically a metal. It can be dielectric. In our case, whatever the work which I'm going to discuss with you, so mostly we have used metal, the aluminum basically. Okay, so this is a metallic ring, and technically you can say it is a split ring resonator. So it can be understood in terms of LC resonator, LC frequency, inductive capacitive resonator, that we keep learning from our school days. So from where this L and C comes. So you can see a gap in this ring. So this gap is basically contribute towards the capacitance. And the size of this ring is basically responsible to provide the inductive property to this ring. So the in a way, in an engineer point of view, this ring acts as LC resonator, inductive capacitive resonator, that I've shown in the picture. As you can see, as we repeat these rings, so basically we are getting an array of the LC resonators that you can see in the picture, right? So that's how the basically the basic meaning of a unit cell, metamaterial unit cell, and how does it look in terms of engineering point of view. Okay, so in terms of fabrications, this can be used, this can be fabricated with lithography. Basically, I have used photolithography in my case, where we have used silicon wafer, and then you do the spin coating with a photoresist chemical, and then you basically expose your photoresist coated silicon wafer using ultraviolet radiation. That is this technique basically known as ultraviolet lithography or photolithography. So basically, uh, for example, you make a design, right? So you first of before that you have to make a mask. Okay, so the mask is having the details of the structures which you are going to print or you are going to fabricate. So you put your mask here, you have the silicon wafer in the bottom of that mask, and the ultraviolet radiations are coming, and they go through the mask, and they basically print that pattern on the device, basically the silicon wafer where which you have put in the bottom. So that depends what type of resist you are using, whether it is positive photoresist or negative photoresist. Accordingly the basically the chemical reaction happen between the ultraviolet and the this photoresist, and accordingly the basically the design gets printed. So later you develop that your printed basically the exposed silicon wafer in a solution, and then you go for the deposition of the metal, and finally you do a chemical lift-off process to realize the actual design. So this is a broad overview how the fabrication happens of these devices, right? And after getting fabricated, because you have to test your devices, so the as you are working in the terahertz frequency, so this is known as terahertz time domain spectroscopy technique. So broadly, how we test the devices. So you have a laser, normally a femtosecond laser. So that laser strikes basically with a transmitter, a photoconductive antenna, which we have used in our case. So the laser strikes with the photoconductive antenna. uh, okay, and because of the excitation of the charge carriers in the photoconductive antenna, and because of the excitation and the de-excitations, terahertz are emitted. So one part of the terahertz you focus using the mirrors and passes through the sample, basically the design which you have fabricated, and another part of the tera of the basically the signal that directly go to the detector end. So in a way, you are getting a signal straight to the detector, and one signal you are getting which is passing through the sample. So you compare both the signal, and you understand like how much the signal is basically modulated uh, when it is passing through the device, basically, right? So and normally in the time domain, the signal looks like as shown in the picture in the red color, and then you convert the signal into the frequency, where you can basically understand the different optical parameter like transmission, reflection, absorption with respect to the wavelength or with respect to the frequency, right? And yeah, so you convert your signal in the frequency domain using Fourier transformation. Okay, so this is how broadly the basically the testing of the device is being done. Let us come to the some examples. Like, so I'm discussing the first basic case, like you are having a single ring, right? So this ring is having a single gap. So this is, as I have told earlier, this is a split ring resonator, and this ring is having single gap, right, as you can see in the picture. So 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 as you know, this ring is acting as a LC resonator, right? And in our school days we heard a simple formula, like capacitance is defined in terms is equals epsilon A upon D, right? A is the area and D is the size distance between the plates of the capacitor. So as you can see here, the size of this gap is basically acts as a distance between the plates, right? And so and we also know frequency can be defined in terms of 1 upon 2 pi under root LC, right? We learned this also in our school days. So you know, here here what I have done, like we have basically changed the size of this gap. So G basically represents the size of the gap. So I have tuned the size of this gap from 4, 8, 20, 26, 30, 36. The units are in the micrometer. So whatever the dimension I'm going to show, because we are working in the terahertz frequency, the units are basically in the micrometer. Okay. So as you can see, as we increase the size of the gap, as you can see in the picture, so the basically if you increase the size of the gap, because the capacitance is inversely proportional to the gap size, so capacitance is basically going to decrease, and as capacitance is going to decrease, the frequency is going to increase. So you can see in the graphs, with increase in the size of the gap, frequency is basically blue shifted. It is basically increasing as a function of the gap size, right? And it is happening both in both polarization, when the if the polarization is perpendicular to the gap or the parallel to the gap. So here we are defining, because we are like interacting our device with the terahertz frequency, which is basically an electromagnetic radiation, right? So an electromagnetic radiation consists of electric field, magnetic field, and it's a wave vector. So here we are defining the polarization in terms of the electric field. So if I'm saying I'm talking of the perpendicular polarization, it means the electric field vector is perpendicular to this gap. And if I'm saying I am discussing the parallel polarization case, it means the electric field vector of the terahertz radiation is, yeah, along the basically the gap along the gap. Basically, it is parallel to the gap. Okay, so you can see in terms of the basic equation, we can understand a single, I mean, a split ring resonators, and we can basically understand its transmission properties. So this is a simple case, right? So let me come to a case where the unit cell consists of more than one units, more than one basically designs. You can see here the basic unit cell consists of uh, two rings, the inner ring and the outer ring. So what we have done in this case, as you can see in the pictures in the right hand side, there are like 6 pictures. So which are named as mm1, mm2, 3, 4, 5. So it means metamaterial 1, metamaterial 2, metamaterial 3, like that. So what is the basic? If you see the mm1, if you see these 5 pictures, though, you can see the inner ring is basically the closed ring, and we have put a gap in the outer ring, and the gap size is going to increase. You can see in mm1 the gap is basically of the 0 size. In mm2 the gap size is 6 micrometer. Then you can see the gap is basically increasing, right? 12 micrometer, 20 micrometer, 36 micrometer. So we have made 5 devices where the inner ring is kept as a closed ring, and the outer ring that is being opened, and we have put 2 gaps, and we are like continuously increasing the size of the gap in the outer ring. So in a way we are getting 5 devices, and these are basically the pictures from the microscopes, the fabricated pictures, fabricate the micrographs which I have put here. Okay, and this work is published in the Plasmonics, so you can have a online view of this work as well. So this is the basically the transmission study of the devices, of the 5 devices, mm1 to mm5. So right, the left hand side picture, so the measured results which is being captured using terahertz time domain spectroscopy. Right hand side shows the numerical modeling results which are being pursued using CST Microwave Studio. So there are many tools like NSYS Numerical Console. Yeah, there are different tools which are being normally used in the modeling of the devices. For my case, I have used the CST Micro Studio most of the time. Yeah, so you can see I am claiming these devices as a broadband devices. Why? Because you see, you see the basically the left hand side diagram where we have shown the experimental results. So for the MM1, where the both rings are closed rings, so the results are shown with the black curve, right? So you can see the black curve. Basically, we have a resonance around zero point 0.6 terahertz, then there is a peak, and there is another resonance around 1.4 terahertz. So as we increase the size of the uh, as we go from mm1 to mm2, mm3, mm5. So mm5 means we have the outer ring of the maximum size, right? So we are, that is being shown with the green curve. You can see the green curve in the left diagram, basically. So what is the difference between mm1 and mm5? So in mm1, that is being shown with the black curve, there is a resonance deep around zero point 0.7 terahertz, then there is a peak, then there is another resonance deep around 1.4 terahertz. But in the case of mm5, that is shown with the green curve, there is a single resonance, a single broad resonance. You can see, so from while going from mm1 to mm5, we are getting a single broad resonance, you can see, and that are being spotted with the numerical results. So that's why the design is basically named as a broadband metamaterials. So here we are getting a blue shift in the first resonance from 0.74 to 1.6 terahertz, and bandwidth enhancement from 0.39 to 0.82. So for MM1V, the resonance bandwidth is 0.39, and for the green curve, it is increased to 0.82. Okay, while the second resonance remained at the same position. You can see why the second resonance is remaining at the same position, because we are making changes only in the outer ring. We are putting gaps only in the outer ring and increasing the size of the gap, but we are not making any kind of changes in the inner ring. That's why whatever the resonance that is being coming uh, because of the inner ring, basically the second resonance around 1.4 terahertz, that is basically originated from the inner ring, that is being remains constant because we are not making change in that, right? So this kind of results we can understand in terms of the basically the interaction of the radiations with these devices, how the charge carrier are excited, what is the nature of the excited charge carrier, whether they are arranged in the dipole type of configuration or in some other configuration. So we can understand in terms of the excitation of the resonant mode this kind of results. So I have shown here the surface current picture where you can see for MM1 device around first resonance 0.69 terahertz, the basically the outer ring is being excited, while for 1.35 terahertz, the you can see the red curve arrows are dominating in the inner ring. So you can see at one frequency outer ring is excited, and another frequency inner ring is excited. So in this way we can understand how the basically the interaction is happening with the terahertz with the devices, and we can understand the nature of the resonance and basically the origination of the resonance. Okay, so these are the results which are being achieved from the CST, right? In this way you can understand the distribution of the surface current for the other polarization case also. Okay, so this is basically one work which is being dedicated towards realization of the metamaterials for the broadband terahertz applications. So another work that is on the sensor side. So the previous work is basically a planar work where the designs are in the basically in a plane, in the XY plane, you can see. So here basically we have used to explore metamaterial for sensing applications. So here that basically it is a multi-layer design. So we have a silicon wafer, then we have grown these rod type of resonators, then we have a polyamide as a spacer, then we have another layer of these rod type of resonators. So basically the bottom layer and the top layer that are being uh, joined with a polyamide, basically a polymer, basically. So what we are going to do, we are basically tuning the thickness of this polyamide, and we see how the response, how the basically the transmission response of the device is being changed. So you can see in the graph here where amplitude transmission is being studied as a function of the frequency for the two thickness value, 2 micrometer and 4 micrometer. Okay, as you can see, there is a shift in the resonance, and the second resonance you can see around 0.87 terahertz, that is being a a sharp resonance. Technically it is a phenoresonance, and that as you can see, the sharp resonance are helpful for the sensing application. We have explored this resonance for the sensing applications. So this work is being published in the Physical Solidi Reference Letter and selected for the cover page of the journals. And finally, then later we have extended the technology and filed and published a patent, basically that it is granted by this time the Indian patent on this work. Okay, so the discussion you can see more discussion about this work on the in the online. So broadly, you can see this is one of the work where the metamaterials are used for the sensing applications. What is the novelty of this work? Why it is being selected for the cover page? Normally the designs which are being used for the sensing application, they should have the sharp resonances. And normally the way to excite the sharp resonance, one of the way to excite the sharp resonance is to break the symmetry in the device. Here you can see the the designs, the top layer and the bottom layer, they are of the same, they are of the same design, same symmetry, because we are not breaking the symmetry as per the design, right? The whatever the bottom layer, the similar is the top layer. So you more details you can have of this work in the on the online version of the article. The another work where the metamaterials are used as a switch. We know what is a switch. Basically in our home we use the electrical switch where like on off. Then for example we make the fan on, right, by pressing the button, the basically the electric switch. So in the similar way metamaterials can act as a switch. What I mean by metamaterials as a switch? It means metamaterial shows a resonance. If the resonance, if it is showing a resonance, it means it is on, right? If it is not showing a resonance, it means it is off. So metamaterials is also act as a switch, the resonance on, resonance off, like that. So let's see how it is happening. So here the unit cell consists of two resonators. So basically in this unit cell, two resonators are there and both the resonators are having one gap. Okay, so what we have done, this is an active work. What do you mean by active work and passive work? So earlier work I have shown, like the first work where I have studied five types of sample, mm1 to mm5. So there we have fabricated five devices. And so instead of, so for the experimental, for the real-time applications, for example, so we want a device, a single device which can do so many works. So here instead of fabricating so many devices, we have fabricated a single device, and basically we have control its parameter actively using optical means like optical laser. So what we have done, first we have basically pump these devices using a laser. And because of the pumping, because of the pumping of the device with the laser, so the charge density environment of the device, because this is metal, right, aluminum, and the below is the semiconductor. So whatever the charge carriers, the free charge carrier excitations in the entire devices, that gets modulated. Then you basically incident the terahertz on these devices and study the transmission. Okay, so depending on the different power of the laser, right, which you are going to use to pump these devices, the different amount of charge density gets excited in the device, and then the response of the device gets changed. We will show in the next slide. So this work is published in the Journal of Optics. So here you can see here we have used like five power value. I have shown the results for 0 milliwatt, 2 milliwatt, 4 milliwatt, 5 milliwatt, 10 milliwatt. So for the 0 milliwatt case, so you can see here the black curve showing the basically the experimental results, then the red curve which are being done using CST Microwave Studio. Okay, and you can see they're quite appreciably matching. So you can see, so basically as with the different laser power, what is happening in that device? Basically the electrical conductivity, basically the charge density concentration in the device, that is being basically modulated. So you can see for different powers, different electrically conductivity value is being shown, like 0 milliwatt, 2 milliwatt 77 per meter, 4 milliwatt 97 per meter, like that. So what is happening at 0 milliwatt, you have a single resonance of the devices in zero point 0.2 to 0.8 terahertz. Then you slowly increasing the power to 2 milliwatt, 4 milliwatt, 5 milliwatt, 10 milliwatt. So you can see around 5 milliwatt, if you compare the picture, uh, 0 milliwatt and 5 milliwatt, basically the black curve you can see, so that is basically blue shifted, and that is basically getting broadened also. And as you see for the case of 10 milliwatt, the resonance is no longer there. So for the 0 milliwatt you have a resonance, for the 10 milliwatt you don't have a resonance. So device is acting as a switch, a metal switch, and you are controlling that switch actively. you are making in terms of the laser power, right? You have 0 milliwatt, you have 10 milliwatt, you have a resonance, you don't have a resonance. So as a whole, the device is acting as a switch, right? So you can understand these results in terms of the surface current and the electric field pictures. You can see for the 0 milliwatt case, there is a, you can see there is a concentration of the electric field around the gaps, because the gap is acting as a capacitor, and you know around the capacitor plate we have the charge carrier concentration, right? And for the extreme case, 10 milliwatt, uh, in terms of the modeling, you can say around 4000 Simon per meter conductivity. You can see that there is no any concentration or the excitation of the charge carrier. So resonance is there, resonance is no longer there, like that. Okay, so that's how you can see broadly here metametals are used for the broadband applications, for the sensing, for the switch. They can act as a switch, right? So there are many other fields which are currently open, in the terahertz we can see, like terahertz spintronics, terahertz nonlinear devices, wireless communication, of course the terahertz sources, terahertz detectors. Okay, because broadly there is a source, there is a detector, and you put your device in the between, right? So there are different scopes, right? You can basically develop different kinds of terahertz sources. In general, any sources, you can work on the terahertz detector side. You can work on the middle part, metamaterials. Okay. uh, so these are different fields where you can focus during your research, maybe you during your PhD, during your postdoc, in which side. So most during my PhD I have worked on the metamaterial devices. Currently I'm working on the this side and this side, right, like that. So this is a broad domain, right? So yeah, so broadly we can say metamaterials are a great candidate to control and manipulate that electromagnetic waves. Here I have studied terahertz waves mainly, and they can be helpful to bring many applications in the terahertz frequency, like modulators, like sensors, like switches, okay, and filters. So they have broad, they have the potential to basically push the technology in the terahertz frequency range, right? So yeah, with this I acknowledge our team members, our collaborators, and of course the potential audience of today. And there are pictures which I have taken for the illustration from the internet and the web links. I acknowledge that. So for the online version of this article, you can go to my Google Scholar page, where you can have a detail of these results in the published works, right? Yeah, so with this I conclude my talk, and thanks to the organizers. Jai Hind.
Hello? Hello?
Yeah, hello.
Yeah. So from the participant, any question is there? Any participant want to do any research work or any collaboration work? They can unmute themselves and they can ask the question. Okay, just I will ask the question. Actually, we are working on photonic crystal, we are working on SPR, we are working on LDR. So the thing is, we are telling that biosensor we can do, in forensic we can do sensor technology. So the thing is, anywhere till now it is not commercialized as per my knowledge. SPR based sensor or plasmonic based or photonic crystal based. So, what is your opinion about this?
Yes.
Although we know that bulk production is very easy and cost effective because of the miniature in size, but what is the reason that till now it has not reached to the common people, common man?
Yeah, so you are right. I mean, technically, like there are different way to excite sharp resonances, like in terms of phonoresonance, toroidal resonance, bound states in the continuum. Yeah, and I think the new I see recently the exceptional excitation of the exceptional points. So where also the sharp features are there. So yeah, in terms of the commercializations, some works that are being come where this wearable devices that are being put on the skin, and they can detect the different elements in the body basically. uh, uh, yeah, as far as the technical this commercialization is concerned, of course the scalability of the devices, and because in the terahertz frequency you require devices in the micrometer range, right? Of course there are challenges, I mean, to fabricate the devices, because the dimensions are quite small and compared to the gigahertz frequency where we have the dimension in the millimeter range, right? And yeah, of course there are like progress in the lithography techniques in these days, where you can go up to these smaller dimensions. So with time I see the devices are being getting popular, and they're coming for the commercialization. Of course there are challenges, of course, because the work which I have shown to you, they are basically metallic based devices. If you go for higher resonance with high quality factors, people are trying with dielectric metamaterials or the superconducting platforms to excite sharp resonance. So again, I mean, the basically the response from the devices, and how good your samples, the quality of the samples, that again, I mean, there is a concern and a challenge as well. Yeah. Soon, I mean, the device, I mean, the things are getting popular, and yeah, some works I have seen, like where they are put on the for the biomedical stuff on the skin, and to track the different like pH value of the chemicals in the body, like that kind of stuff I have seen. Yeah.
So, in your knowledge, anywhere you have seen the packaged sensor and ready-made it is available, like thermometer is available in the market, like any other sensor,
Okay.
pregnancy kit, like that. That is also a sensor. When we'll put one drop of urine sample, it will become two line. It means it is positive. So, like this are available in the packaged one. Out of curiosity, I am asking this question.
Yeah, so I think, I mean, so far, as far as guess, I mean, they are being demonstrated to the laboratory scale, as far as the initial testing is concerned. So large scale commercialization, I think that is still in the progress for the society purpose. That's, I think.
Thank you. Thank you. That is the reason many people are working towards this to make this as a commercialized one.
Yeah, yeah, you're right, man.
So from the participant, he is a very good resource person among all 15 speakers. So yeah, and he is very hardworking. If our student want any internship to do online internship, now many university are offering online internship.
Yeah,
So
so uh, we have students here like doing internship from the university itself, and I think from the other countries as well. So you can directly email to the professor saying the period of your duration, and you are like interest with the work done here. And of course they allow, and people come here to do the internship. So just email to the professor and ask what is the feasibility to do that. And
yeah,
there are
so that
programs, DARD fellowships in the Europe, where I see the people go during their MTech time, and during the I think PhD itself. So for 3 months, 6 months, that kind of stay they do, and
so
do the
online
research.
is
There are
possible. Online, so that throughout the
online.
world people can join and people can, like somebody will give online internship.
So online internship, as far as the
Yeah.
devices concerned, so mainly they can guide you if you're doing some modeling work. I think
Modeling, simulation.
modeling work, modeling simulation. Yeah, that can be I mean done in terms of collaboration, and you can start working from there, and away meetings in between. Like that, that kind of work is always there. That can be done. Yeah.
Thank you. Thank you so much for giving your insight about this topic. And not only that, you are helping for our student also. So I
Yeah.
have your
Yeah.
email
Please.
ID. I will write a mail to you so that you can
Yes.
guide our student who are interested and
Yeah.
looking
Yeah.
for the internship.
please feel free to reach out me. I can be of any application to the society. Yeah.
Okay. Thank you. Thank you. So I
Thank you,
think
ma'am, and thank you your entire team for the dedicatedly effort this good event and for the kind invitation.
yeah.
All.
So formal way, I will tell Asha madam to end the discussion. Asha
Yeah,
madam,
sure.
yes.
Yeah.
Any
Uh,
question is not there, na Asha madam?
no, ma'am, no questions.
Okay. And you announced this also that today afternoon session it is mandatory. All the participants should be there as our
Uh,
principal sir will address
okay,
to everyone, and then uh, uh, feedback link will be shared at that time.
okay,
Okay.
okay.
Uh,
Yeah.
At the end, you
Uh,
tell first you and wind up the session.
sure, ma'am, sure. Ma'am. On behalf of the Oxford College of Engineering, I would like to extend profound gratitude to Dr. Deepak Kumar, currently serving as a research fellow at the School of Electronic and Electrical Engineering, University of Leeds, United Kingdom, for graciously accepting our invitation and delivering outstanding session on the subject of metamaterials in photonics. Dr. Kumar also imparted valuable insights to our participants regarding the procedure for securing admission to postdoctoral programs in esteemed institutions. It was indeed a privilege to learn from such an esteemed expert. We sincerely appreciate your presence and contribution to our event. Thank you for joining us today. Thanks a lot.
Thank you, ma'am. Yeah. So with this,
Thank
I
you.
conclude from my side. Yeah. Thank you.
Thank you.
Thank you. Thank you. Thank you.
Yeah. Request to all the participants, please join the afternoon valedictory session at 2 p.m. and it's mandatory to join. And and also we would like to ask you for your feedback during the session. Please feel free to share your feedbacks as well. Thank you all for joining the session.
Asha madam, you have identified the who will give the feedback and all.
Yes, ma'am. Some people have come forward and given their names. If anybody else is interested, even they can join now the session
So
and they
today
can
again
give
I
the
am
feedback.
yeah. So among you who and all are joined, and we were thinking because today is the last day. So can you on your camera so that we can take the photograph, all of you? How many of you are possible? Just you on the camera. Yes, I can see Rajendra Tiwari. Welcome. After a long time, I am seeing you. Right now, you are in Lucknow, correct?
Yes, ma'am.
Okay.
Yes, I'm
Very
in Lucknow.
nice. Very nice. So, okay, many people join. So, so anyway, feedback and all we will take. Just informal way, I am asking. That time, principal will be there. Now he is not there. So, I am asking how it was. 15 days, and today is the last day. Anyone? Yeah, Rajendra Tiwari, I can ask you.
Yeah, ma'am. It's a really very informative and learning session we have got during these 2 weeks FDP, and really we have learned a lot of things. We get a chance to just listen very good speakers, eminent speakers during these sessions, and we have got certain ideas during their session that we can proceed further with in the implementing them as research papers. It was a really good session, ma'am. Thanks.
Actually, I asked him. He was my scholar, and from MIT University, and I have given this time opportunity for the youngster also to give a talk. Not only we old people are occupying the always, so we should give the opportunity to youngster this time in the speaker, I think you all have seen that many youngsters were there, and they have given very nice actually talk. So next time this group will be there with me. So anyone is interested, we will tell and we will give opportunity to give talk. Okay. So Ranjit, you have joined. Ranjit Goda.
Yes, ma'am.
Thank you. So evening time, afternoon time, 2 o'clock, all of you join, and that
Yeah,
time our
definitely.
principal will also join. And kindly you share your experience. So one of the speaker was Dr. Ranjit Goda also. So you see how nicely he has given. So we have to give opportunity to youngster also. This is what I believe. So because they have done the research in that area 4 5 years, so definitely they have more knowledge. We should give the opportunity. I am trying to give the opportunity now. I am whenever I am getting opportunity to give talk, first I will ask my scholars. Scholars now no more they are scholars. Now they are doctorate. So I will ask them, and if they are interested, they can give. So from outskirt also I will ask if in the group I have the everybody's this one in the group contact. So we'll see in future. Thank you very much for joining all of you. Okay, Asa madam, you have taken the photograph.
Oh, yes, ma'am. Yes, ma'am. Today we have got very nice photographs.
Thank you, thank you. Few photograph you post in the our WhatsApp group also.
Sure, ma'am.
Okay, so that even they will have the photograph. Okay,
Yes, ma'am.
so
I'll share.
we will meet all of you in afternoon 2. Huh? Okay,
Thank
that
you.
time I will just ask because it will be a formal way. I will ask to introduce yourself. If possible, you can on the camera and try to introduce yourself. Okay, okay. Thank you, Asa. Now we can wind up.
Yes, ma'am. Yes, ma'am. Sure.
Okay,
Thank you.
okay, bye.